be gone tomorrow because I have to go to a funeral, which is kind of an icky reason to be gone, but it is what it is. So anyway, I'm not going to be here tomorrow, so I want to get through as much of the real content stuff while I'm here as possible. And then Ms. Gribble is going to be here, so you totally luck out, because not like the regular sub person who gets paid to do it, but then she has the opportunity to be here anyway, and knows physics, right? So that's like double bonus for us. So that means that she will work through a few things with you tomorrow, but I'm going to kind of lay the groundwork today. Does that make sense? So that's why we've kind of switched plans a little bit. So tomorrow you will work on some problems. Tomorrow you will finish your friction lab, and tomorrow you might also start kind of a lab activity as well. So there's like lots of stuff to be done tomorrow, but it's stuff that I feel like she and I talked a lot, and she's going to be good to lead you through. Okay? So today we're going to do more like focused notes and some conversations and things like that. All right? So we're going to start with this one problem. And it's kind of a mystery box, except it's a little bit of a mystery box because I wanted to make sure that I was able to actually hold it up. And so it says that a box is being held in place against a vertical wall by a hand applying a horizontal force. So this isn't actually my mystery box, but I'm going to use it because it's a box and it's in front of me. Okay, so this is the situation. So you want to watch up here, right? So I've got the box. I'm going to push against the wall. I'm going to hold it like this. Okay? So my force is horizontal. I want you to draw a free body diagram of that situation, and then determine the magnitude of all of the forces acting as best you can. Okay? Give that a shot. It's a little bit of a thinker. Yeah?
Is it on the surface of the floor too?
No, it's like this. So I am demonstrating the picture right here, but I'm not going to do this for 5 minutes. So look now. Everybody see it? I'm pushing this right there. Okay? All right, I'm done. My arm hurts. All right. So go ahead and start that problem. So you're going to draw a free body diagram of the situation, and then see how many forces you can figure out. And then that'll kind of lead us into our conversation for the day. Okay? So give that a shot. I'm going to do the fun things like take attendance and that sort of thing. So we're going to start with a free body diagram. You've drawn a free body diagram on your paper, I hope. So let's do that. So I have not, so let me do that. That would be fun. Okay, so I'm going to draw the box. Now, in its purest form, a free body diagram really should only have one object. It really should just have that object. But because we're learning and because we just need a little context, I'm going to go ahead and draw the wall in here. Is that okay? So it's not like, if you were doing an AP test and they asked you to draw a free body diagram, they'd probably give you the dot or give you the box. But it's okay to draw that wall. So I'm going to go ahead and put my wall right here. So there's my wall, just so that we know kind of which direction things are going at. Okay, now that I've got my box and my wall, I need to know what forces are acting. Who's got a force? Ooh, pick me, Miss Carbine. Go, tell me.
F of hand on box pushing left.
F of hand on box pushing left into the wall, right? So everybody okay with that? Yeah. Cool. So we're going to go in this way. F of hand on box. And what kind of force is that? The applied force. Remember, we had that bright red pink sheet. If you don't have that out, you might want to get that out because we're going to write some stuff on there in a minute anyway. So F of hand on box kind of needs to be from the center of that dot, so I'll just make that dot bigger. Now it's from the center. All right, that's one. Go, Bo, what else you got?
Normal force going to the right.
Normal force going to the right. What do you think? Do you agree with that? Is that okay? Yeah? Normal force going to the right. Did anybody have an issue with that? Oh, and it's not, so you said it's the what object?
Surface on
Yeah. So surface, and you could call out what surface it is if you want. Yeah, but you don't have, you could say surface. So the force of the wall on the box, and that's the what kind of force? Normal force. Bam. Awesome. Okay. Did anybody have any kind of issue with that normal force going right or left as opposed to up and down? It makes me happy if you didn't. If you did, I'm like, oh, because a lot of times people want normal force to go up and down because usually you're looking at the frog or the ball or the box or whatever sitting on a table, right? In which case the surface is pushing up and it's pushing against the gravitational or the earth pulling down, right? But in this case, because the surface is vertical, then The wall is going to push, in this case, to the right. Yeah. All right. That's two forces. What else you got? Anything else? Anything else acting on the box? Morgan, do you have anything else? Gravity. So that's the force of the Earth on box. Which way does that go? It goes down. Bless you. FG. Cool. Anything else?
Friction against the wall going opposite gravity.
Friction again.
Force of friction.
Force of friction. You said something else and I didn't quite catch what you said, so I was just like wondering what you said. So which way is it going, you said? It's going up. Cool. So the force of the surface, or the wall, I guess I wrote wall there, so we're going to stay consistent. So I'll say the force of the wall on the box. Oh, hi. I literally just put a new battery in, so I don't know what the deal is. Okay. Yeah?
Why is friction going up?
That's a really good question. A totally valid question. Why is the friction going up?
Because it always goes parallel to the surface. So it's parallel to the wall.
Does that make
Is
sense?
that because the gravity is pulling the box down?
Because the gravity is pulling the box down, and this is the conversation I was hoping we would have right now. So I'm going to say, number one, thank you for asking that. Number two, I'm going to go back to this was our conversation, right, yesterday, about friction. Does this look familiar to you all? Okay, so when we talked about this, we said that the force of friction was the surface on the object always acting parallel, right? So that's part of it. And then, so it has to go either up or down. The key here also is that it opposes motion. So you can kind of think about it, if friction wasn't there, if there were no friction, where's our box going to go? It's going to go down, right? So the friction's the thing that's going to hold it in place, it's going to keep it up. Yeah. Awesome. All right. Bam. Okay. How are we done? Are we good with that? Anybody want to, I want to know if you don't feel good, because I want to help kind of ferret things out. Are we happy? Okay, now let's determine the magnitude of all the forces acting. That's a lot to do. How are you going to start? Where did you start? I'm going to ask for the back table because I haven't talked to you guys yet.
Well, you could start by saying the net force is 0.
How do you know that the net force is 0? F net is equal to 0. I guess that's because it's not moving. And then what question am I going to ask? Yeah. Really, the reason is because it's not accelerating, right? So the thing that I want you to keep in your brain is, it's not moving. That's true. I totally agree with that. But because it's not moving, we can also say it's not accelerating. And the thing I want you to have in your brain is, can you have a net force of 0 with an object that is moving? 100% you can, for sure. So the thing that we care about is the acceleration. But in this case, it isn't accelerating. You're right. Okay, so I know that the net force is 0. That's a good place to start. Now what am I going to do? Keep going?
Can you do the force of the Earth on the box?
Sure we can. That's one that we can actually calculate, right? Yeah, so we can calculate the force of the Earth on the box. So the force of gravity. And how do you calculate the force of the Earth on the box? Go, TJ. Mass times acceleration due to gravity, right? Yeah, so you've got, what is that, 1.5 kilograms times the acceleration due to gravity is, indeed, meters per second squared. We do some fancy multiplication. If you don't have a calculator out, you'll want one today for sure. So go ahead and get one out. Everybody plug it in. Everybody have some fun. 1.5 times negative 9.8 meters per second squared is 14.7, says the back. Do you guys agree with him? That's a good question. Is it negative? So it says magnitude. It's a good call, right? Is it negative? So it depends on which way you're going to look at it. If we're talking about just the magnitude, then it wouldn't be. I'm going to write a negative in there just for now, just to kind of acknowledge that it is. But then if we're going to write this answer, then we're going to FG is equal to 14.7. Is that okay? The magnitude. But I'm going to write that negative so that I don't forget. I will tell you, friends, that if you are given a question and it asks you to calculate something and it asks you for the magnitude and you put a negative sign, I would never count that wrong. Okay? If you forget a negative sign when you're supposed to have one, then it can cause trouble. So that I put that here just because I wanted to be able to compare our numbers. Chris, go.
Will the AP test get mad at us if we call 92 negative?
think so, because I don't think that they would ever explicitly ask for it like that. Does that make sense? I will keep my eyes out for it, and if I find something that is a counter argument to what I just said, I will let you know. Deal? Okay. All right. So I got 1 out of 4 done. Yay for me. Okay. Any more? That's only 25%. I'm not passing yet. All right. Go, Chris.
You said that the force you were using was 2 newtons, so the force of the box and the force of the wall of the box was 2 newtons.
Okay, so I can see the applied force is 2 newtons. I'm okay with that. Okay, and if we're talking about positive and negative, we might call that a negative force if we're talking about the direction. Are you with me there? Right. So I'm going to put a negative by that just to be talking about. So this is going to the left. Okay. Why is it 2? Yeah, because and if you read the question early on, I didn't say that because I was slacking, right? So it's going to be 2. All right, there we go. All right, so that's my applied force. So now I'm 2 down, so I'm not quite passing yet, but I'm getting closer. Get me even closer. FA is 2 newtons. Go, Bo.
So are you not multiplying by the mass for the normal force and the applied force?
So I am not, but let's figure out why. Does that sound okay?
Yeah.
So newtons is a measure of a force, right? So anytime you see newtons, you know that that's a force. When we have a 1.5, that's not a force because it's in kilograms. So that's just a mass. That's just how much stuff something has. The only way to get to the force here is to multiply that by an acceleration, right? So the acceleration times the mass gives you a force. Does that make sense? This one's already a force.
Okay.
Does that help what
No,
the question was? Okay. All right. Okay. 2 forces down. 2 to go. Gotta use good physics here, friends. Yeah?
Normal force also equals 2 newtons.
How do you know that? It doesn't say it.
Well, if it didn't equal 2, it would be either moving left or right.
Okay. So we need to use some explicit physics here to articulate kind of what you just said. So, and this is the thing that College Board is going to look for, right? This is the thing that we want to make sure we're really being explicit about. And this is the thing that is on that gold sheet that we're going to talk about in just a second as well. Is FA, that's given to us. We know that that is 2 newtons because it's set it up there, okay? But the next part, we have to actually explain how we know that it's not accelerating. We know that in the x direction, the net force is equal to 0 because it's not accelerating in the x direction. Everybody good so far? Okay? So that's the first piece. You could write this as F equals the mass times the acceleration in the x direction, and oh my goodness, the acceleration is 0. That would be like the super thorough way to say that. Okay? We have to say this explicitly. If you don't say this, and you just put FA is 2, and you put FN is 2, and you just like smile and wave your hands, I'll wave my hands back at you, but I won't give you points for that, because that's not going to be enough. That's not a complete enough answer. So you need to say F net of x is 0, and you can put this in there or not. That part I'm not going to sweat about. And then you also need to say that, oh my gosh, net force in the x direction is going to be all the forces acting in the x direction. So that's going to be, if we add them up, we've got Fn, and we've got Fa, right? They have to add up to 0. Now we can put our Fa in here, our negative 2 newtons. And that's why I want that negative in there. Plus Fn is equal to 0. And that is why Fn has to be 2 newtons. Okay? Just saying that it's 2 as an intuition, right? I mean, that is good intuition, but it's not going to get you that full, thorough answer. Okay? We doing okay? All right. Now we're 75%, so we're passing. So good for us. But I want to get an A, right? I want to get all of it right. So we've got 3 things done. We need 1 more. What are we going to do?
We do essentially the same thing we just did, except we solve for the force F of x.
So we do F net, but now in the y direction, right? So we say the mass times acceleration in the y direction. Oh my gosh, A is 0 because it's not accelerating. It's not moving, so it's not accelerating, right? And then we're going to say, okay, so that's F plus Fg. So we've got 0 is equal to Ff plus a negative, what was it, 14.7. So, oh my gosh, FF then has to be 14.7 newtons as well. Okay? In this problem, these two things are by far the most important pieces. Okay? These are the fundamental pieces that make this a thinking problem. Okay? That make this a good physics question. Okay? How are we doing? We okay? Yeah? I can't read your faces yet. You look all happy-ish. Sweet. Okay. I want to take just a moment. I'm not going to spend a lot of time on this, but I want to take just a moment now that you have gone over that workbook 2C page for you all to talk through with your table mates this stuff right here. This is kind of like a two-column proof, right? Remember those from geometry? You love them from geometry, I'm sure, right? No, maybe not. I don't know. I want you to make sure that you can explain each of these steps. This is very similar to the question we just did. I'm going to give you 3 minutes to discuss in your tables the answers to those pieces. Go ahead and do that. We are going to get started here because I want to make sure that you're understanding. I also don't want to get too far into things and, lose track of what's going on. I was having a great conversation in the back of the room, and I just wanted to explain to you all kind of what we came up with because it really is important. There are 2 different ways to find FNet, or 2 different definitions for FNet. One is mass times acceleration, and one is adding up all the forces, okay? When you're solving all of these problems, you have to do both. You have to have mass times acceleration, and you have to have all of those forces added up. This equation right here, FNet equals 0 equals FF plus FG, is not true every time. It's true in this case, okay, because of the way we drew the free body diagram. So in order to get an FNet equation, you don't look at your equation sheet. Your equation sheet will not tell you what FNet equation to write down. The only thing that tells you what FNet equation to write down is the free body diagram that you've drawn, okay? That's where you get the information. That's kind of like your given setup in order to answer the question. Okay, so I just want to make sure you caught that because it is pretty darn important. All right, so on this, I took this from the answers. I just wanted you to take a look here at the kind of the way to think this through. Do you need to have this written word for word this way? For sure not, but this is what College Board says are the right answers. So let's take a look here. So you guys have seen this little summation thing before, right? Yeah, if you've never seen that, if it's freaking you out, don't worry about it. It's okay. It really just means FNet. I write FNet like this because I don't like to scare people. But if you would rather write the sum of the forces, that's sigma, right? Greek sigma. It's right up there. Where did it go? Bam! It's right there. And that just means sum of. So you can write the sum of the forces. If that makes you happier, if you like to be fancy or whatever, go for it. Either one is fine. College Board doesn't care. They like it either way. Okay? So the sum of the force in the y direction is m times ay. We're starting with Newton's law. That's true, okay? Then we say Fn plus Fx is equal to may. They say in the vertical direction there are 2 forces acting, normal force up and gravity down, okay? One dimension is determined by a positive or negative, taking up to be positive and down is negative. Is that okay? Is this making sense? This is like the thinking that goes into this. Okay? This is the kind of narration of what's going on. Fn minus Fg equals ma. Because the box is not accelerating, that means the acceleration is equal to 0. Okay? Same process, big thinking that's happening here. Being able to articulate this is what I want you to be able to do. Again, this is not a plug and chug kind of class anymore. This is all about understanding the thinking, understanding why and how, as opposed to just do it. Okay? We doing all right? So far so good? Okay. We need to add a couple pieces in here into the friction stuff. So go ahead and hop into, we'll go to the back to that later. We're not going to do it right now. I want to go back to the friction notes that we took yesterday. All right. So when we do this, we need to think about a couple of things. Two kinds of friction aside, we talked about static and kinetic friction. We talked about how the static friction increase, peak, and then the kinetic friction is constant. And we need to be able to define that and understand what's going on there. And we have not yet written down an equation yet, have we, for friction? We need to do that. So we need to know what friction is equal to. So we can usually figure out what friction is equal to just by using a three-body diagram to figure out our F net. But there is another way to define the force of friction as well. The force of friction is dependent on two things, and only two things. And given our time and where we're at, I'm going to just tell you what they are. Are you ready? The first one is that the force of friction is dependent on the normal force acting. Does it make sense that if you have a surface, that you have to have a surface in order to have a frictional force, right? And so in order to have a frictional force, we're probably going to have a normal force as well. The bigger that the normal force is, the bigger the friction is going to be, okay? The smaller the normal force, the smaller the friction, to keep it from moving or to prevent it from moving, to oppose motion in any way, okay? So FF depends on Fn, okay? And it also depends on the smoothness or stickiness of the two surfaces, okay? So if you think about it, if I have a frog sitting on a table, okay, Kate, I'm gonna require, you're gonna have to catch the frog, you ready? Okay, so the frog's gonna move, and as the frog travels, there's gonna be some friction between the frog and the table as it moves this way, right? To oppose the motion, so it's gonna be like that, it's gonna slow down. Oh, I didn't push very hard. Let's do it, I totally did it. Come here, here we go. Shh, there you go, now you guys catch it. Right, so it slows down a little bit. Oh, see, there's friction, are you with me here? Yeah, so it depends on the normal force, but it also depends on the surface. Because instead of having this nice smooth surface, what if I colored this surface with, let's say, carpet? And I pushed and he was going, is he going to go as far? Or is it going to be a little bit harder for him to move, right? There's going to be more of something that's going to oppose that motion. And that does not change the normal force. It's changed the stickiness or slipperiness, okay? And the way that we measure that is using another Greek letter. It's like we're doing Greek letter Scrabble today. It's great. We're going to introduce you to a new letter. Do you see, so this is the Greek alphabet up here in orange. Do you see the one that looks like an M? Yeah. Up there, it's not M. It's actually the Greek letter mu. Mu. We spell it M-U. I think about it like a kitty, right? A kitty making a noise. Mew, like a little kitten. You with me there? M-U. Mu is how we say it, but the Greek letter, we use the small one, and it looks like that, okay? So it looks like a U with a tail in the front, okay? So introducing you to a new Greek letter, mu, it's like a U with a tail in the front, okay? And this is known as the coefficient of friction. It's basically how sticky or slippery two surfaces are relative to one another. Okay? That's my very specific description of what mu means. Mu is the coefficient of friction, and it's how sticky or slippery two surfaces are relative to one another. It depends on both surfaces, because if you have, if I covered my frog in carpet, and then I slid it across carpet, it's going to be even stickier, harder to move, right? As opposed to if I have this, kind of nice, soft plush against the carpet, right? So it depends on both surfaces, okay? And it's something that can be determined experimentally, okay? Can be determined experimentally. All right. So So now we need to put this together, because you said, great, Ms. Carver, you told me that FF is dependent on FN and mu. How are they all related? I'm glad you asked. Let me show you. Oops. Come on, silly thing. There we go. The force of friction for kinetic, we're going to do kinetic friction first, is equal to mu times the normal force. It's a pretty easy equation, really. FF is equal to mu times Fn. Quick question for you. Talk at your groups real quick. What are the units of mu? That's a good question, Kurt. What are the units? Wrong answer. Clever answer, but wrong answer.
Newtons to the negative first.
Any gut feelings? Units. Also good answer. Also not quite right, but I kind of like it. If there was a way to work that, I totally would. What are the units of FF, friends? Newtons. What are the units of FN? Newtons. If I have newtons on one side and newtons on the other side, do I need anything in there? I do not. Mu is a unitless quantity. In fact, where it really comes from is that mu is a ratio between FF and FN. Okay? Mu is generally less than 1. Okay? The higher the value, the more sticky it is. The lower the value, the slipperier it is. Okay? So you walking across ice, right, after it's melted and thawed, and it's frozen again, and then you try to walk across, it's really, really smooth and really, really slippery. Mu is very, very, very close to 0. Okay? That's what we're talking about. Okay? Higher value is stickier. Lower is slippery. How are we doing? We okay so far? They're a little perplexed about something, maybe.
But its relationship to FN change depending on what axis it's on, or is it always going to be separate?
It's always going to be FN. So FF and FN are always perpendicular to one another.
Okay.
So this is not, like, we don't pay attention to the directions here. It's just the magnitude. We could write it down as, whoops, like that, yeah. All right. We're going to get that bright pink sheet out. We're going to add one more row. Are you ready? Do you need a bright pink sheet?
Yeah.
I have a bright pink sheet just for you. He's sitting there, just waiting for one. So next we're on the 4th line. The first we're going to write down, anybody want to guess what that is? Friction. Say it with more passion. Friction! Like that? Yeah. What object is pulling or pushing? What'd you say? The surface! What's the direction? Parallel to the surface, yeah. And it always opposes the motion. So those are kind of two pieces that are important in terms of its direction. Its magnitude, well, now we know, right? FF is equal to mu times Fn. We got to throw one more thing in there in just a sec, but I'll leave it like that for a second. Can friction cause acceleration? Yeah. What kind of acceleration does it cause? Negative acceleration. Yes. It causes negative acceleration. Most of the time. I guess we probably shouldn't say it's negative, because it depends on which direction it's going. But it's always going to slow it down. I want to write that instead. Sorry, let me change that. I know, right? You're like, man, she's erasing stuff. This is why I use pencil a lot. Yes. Slows it down. If you draw your surface, if the object is moving this way, then the frictional force is going to be going which way? To the left. How are we doing, team? Everybody happy? Everybody good? Okay. All right. I just realized as we were writing this down that I didn't actually tell you the whole story. Oh no! Can I flip back over to my notes again? Everybody good with that? Sorry. I noticed that I wrote this as kinetic friction. Did you notice that? Anybody notice that? Yeah. I only talked about one kind. Spiders. I didn't talk about the other one too. What's the other one? Static! Static friction is very similar, but it's not quite the same. We gotta write this down. It's still FF. So sometimes I'll write FF sub K for kinetic and FF sub S for static. And a lot of times for mu, they'll write mu sub K for the kinetic coefficient of friction, and they'll write mu sub S for static coefficient of friction. I mean, these are pretty logical things, right? And then we're going to multiply by Fn. So you're like, well, why do we have to change this? This carboning, like, what is the deal? What's so different? Let me show you what's so different. Let me show you this picture up here. Do you remember this, the graph that we saw? The kinetic friction is constant, isn't it? It's always the same. Tell me about the static friction, though. Is it always the same? It's not always going to push as much. It's always just going to oppose something getting started moving. So that means, but it's not going to oppose it so much that it makes it accelerate the other way. Okay? So FF is going to be less than or equal to. And that less than sign is pretty darn important. Okay? That less than sign means a whole lot to me. And I want it to mean something to you too. So I'm going to put a little highlight over that. You might want to get your colored pencils out or your sparkly pens or whatever and take a little note there that, oh my gosh, that less than sign, it kind of means something. Okay? You doing all right? Chris, you look a little confused. Are you okay? You sure? Okay. Real quick, we just got a couple minutes left. I want you to do something for me real quick. You ready? I'm going back to this problem. My question for you is, what is the coefficient of friction acting as I push 2 newtons on this box so it doesn't slip? Can you figure that out for me? Yes, I can. Go ahead and do it. What is the coefficient of friction acting between the box and the surface? Okay, yeah, that makes me so happy. Yes, you can do this. I super believe in you. You guys can do it. Because you know the force of friction, right? And you know the normal force, right? So can you figure out what the coefficient of friction is? Yeah. Yes, I totally can. I got this. That wasn't hard, right? You could even give it to me in a decimal form.
I did it mentally to 215 squared. I was taking my That's what we had. Find out 1.3 repeating.
1.3 repeating?
50 back.
Say what? Okay. Oh. What did I do wrong?
Friction is 14.
Yeah, no, I got it. My numbers didn't work. It's okay. I wanted to tell you guys because I just want to make sure. I'm sorry. I'll fix that in a minute. There is no homework listed yet.